push that rock here with Simpson math. So let's remember science phrases. Y is proportional to x means you have some equation where y is equal to, it's a linear equation, kx, and this is the slope, but it's also called the constant of proportionality, and it just depends on the situation. So now that we remember that, let's look at Newton's law of cooling, which says that the rate an object cools is proportional to the difference between its temperature and ambient temperature. So let's get some variables out here. Let's call T the temperature of the object and T sub A the temperature of the ambient surroundings around that object. And the rate at which this cools, dt, with respect to time. So the rate it cools over time. So little t is time elapsed, and big T is the temperature of the object. The rate is proportional to, so we have K times whatever it's proportional to, and it's proportional to the difference between this temperature and the ambient temperature, so T minus T sub A. And now what we want to do is solve and find the function that predicts the temperature over time, or of the object, okay? So the first thing we're going to do is that separable technique. We're going to get the t's with the t, the big T with the t, and the little t's with the little t's. Well, there's no little t's anywhere, but we'll put it over here with the k. So we have k, multiply both sides by dt, k dt. So I'll multiply both sides by dt, and I'll divide both sides by this. So I have dt over t minus t sub a, okay? Now I'm going to integrate on both sides, but before I do, I'll rewrite this a little bit. So I have 1 over t minus ta. So that's, and then I'll put the dt here. So it looks a little more like integration. And then over here I have k dt. So of course here we get kt, because it's the derivative of a linear equation is just the slope. So the antiderivative of a slope is the linear equation. And don't forget your plus c, baby. And then over here, well, this is just a linear, so we can do crawdad whole, and if it was 1 over t, it would be the natural log of the absolute value of t. But we put in the linear, and then we kick out the reciprocal of the slope, but the slope is 1, so it's just a 1 out here. So I can forget that, and don't forget your plus c, baby. Now, of course, I'm going to subtract this c from that c and get a c over there. So let's go to the next sheet of paper. So I have the natural log, hopefully you can see this, that light's a little bright, t minus ta, okay, is equal to kt plus some constant. Now, how do I solve for a logarithm like this? Well, the e to the value of the log should equal the argument, right? So the value of the log should be an exponent you put on the base, which is e, in order to get this. So I'm going to have e to the kt plus c is equal to t minus ta. Now I want to solve for the function that gives me the temperature of the object, it's not the difference. So I need to isolate this. So we'll add that over. But first we're going to play with that a little bit. So t minus ta. This, remember, we're going to use a to the r plus s is a to the r times a to the s. So this is e to the kt times e to the c, okay? But wait, e to the c is just a constant, okay? And so we'll just, call it cursive c. Okay, so we have cursive c times e to the kt is equal to t minus t sub a, okay? Now what I'll do is add this over. So I have T is equal to the ambient temperature plus C times e to the kt. Now at time 0, the initial temperature is T sub 0, okay? So when this is a 0, the initial temperature, T sub 0, is whatever the ambient temperature is plus C times e to the k times 0 at time 0. Well, this is just a 1, okay? And so I see that T sub 0, subtract this back over, maybe I shouldn't have added it yet, is equal to just, well, this is a 1, is just equal to whatever that constant is. So we're going to call this C in front, since it's the initial difference. This is the initial difference. And so our final answer will be T is equal to the ambient temperature plus that initial difference in the temperatures times e to the kt. And this is the function. So if you give me the ambient temperature, okay, and you give me the, this should have been a subtraction, right? What happened there? Where's my little eraser? I don't know what happened there. Okay, +1 to everybody that screamed at the video, typo, typo, I want that typo point. You all get +1. Okay, so anyway, if you give me the initial difference between the object and the ambient temperature, and you give me the ambient temperature, then this is the function here. And of course, K is dependent on the object itself and all kinds of scientific properties. But if enough measurements, you could plug in, and then you could solve for K, and then you'd have the function. So we solved for the temperature of the object over time as it cools. Math made simple. Some math.